Professor, is everything all set on my end?
Everything seems good on my end. Is everything okay on your end?
Yeah, hold on. Can you speak again, Professor?
Yeah, can you hear me now?
Yeah, okay. I think, okay, everything should be set.
Great. Okay, well, we'll give it another minute because we're actually early today, so. All right, so it is officially 8:30. So we'll get started with some announcements. So as you know, you guys had your first chapter quiz yesterday, and overall, it looks like it went pretty well. And so hopefully now you understand sort of the pattern of the course. So we'll be doing the same types of things for the rest of the term through the other chapters. So there'll be mini quizzes for each of the sections in chapter 2, and then we'll have the chapter 2 quiz, and then there'll be mini quizzes for each of the sections in chapter 3, and then we'll have the chapter 3 quiz. So all the dates are posted in Moodle for the chapter quizzes, and I, of course, will remind you as they're getting closer. But we did pretty good overall. I was pretty impressed with that first chapter quiz. So as I mentioned before, chapter 1 is very broad. So there's a lot of different topics we cover that are not really interconnected. They're meant to be a review, but some of the topics in there are things that people haven't seen, and some of them are things that people haven't seen for quite a long time. So it's important that we touch back on them so that now that we are getting into chapter 2, that we have sort of the skills and language that we need to formalize what we're studying. So starting in chapter 2, which started with limits and continuity, we sort of assume that you've never seen this before. And so that is sort of how we build onto it. If you've taken calculus before, then you have seen it before, but we are assuming that you have not. So we do things in pretty great detail just to make sure that you're understanding it. So we are going to be moving into section 2.1 today, called the instantaneous rate of change. And we are going to build our conceptual understanding in chapter 2 of calculus and what it is and rates of change and things like that. And then when we get to chapters 3 and 4, we're going to sort of formalize our conceptual understanding into formulas and patterns, and it'll be a bit more computational overall once we hit chapter 3. So we're starting with sort of the underlying foundation here of some of the topics we're interested in. And just to circle back to what we did last class, when we talked about limits and continuity, we talked about this idea of closeness. How do we get close to this number? Well, we plug in numbers that are really small that are close to this number. And we're going to sort of build on that in addition to this idea of average rate of change, which we talked about a couple classes ago. So I'm going to go ahead and switch over to the doc camera here. Let's see, that might be. Here we go. Okay. So today we're going to be talking about something called the instantaneous rate of change. And so before we pin down exactly what it means, I just want to talk about it in general. So the one rate of change we know right now is the slope of a line. So we know that the slope of a line tells us how much the function changes in the dependent direction. For every 1 unit, we move in the independent direction. That's the m in y equals mx plus b. So that's the rate of change we're going to be building onto. And we were able to use that before the slope of a line to talk about the average rate of change. And so if we had a function that was not a line, we could pick 2 points and draw in the line that connected them to tell us the average rate of change by using what we know about lines. So what we're going to do is we're going to continue building on this idea of using slopes of lines to help us figure out how to do a better job in approximating how much a function changes. Because while the average rate of change is a perfectly good way to approximate how quickly a function is changing, we want to get to the point where we can figure out exactly how much a function is changing. So we're going to try to move from the approximation into the exact rate of change. That's sort of our goal here. And so in math, and specifically in this class and many classes, you know, what we do when we want to figure out something new is we build upon what we already know. So again, the one thing that I'm assuming you're comfortable with that you already know is just about lines, y equals mx plus b, specifically slope, which is the rate of change of a linear function. That's what we're building upon. And so we started this building when we talked about average rate of change. So remember, when we talked about average rate of change, it tells us how much a function changes on average between 2 points. So we were always looking at the average rate of change between 1 and 5, between 0 and 10, between 2 and 12, right? So we always had those 2 values where we were connecting to make that line. And we use the formula f of b minus f of a over b minus a. And what that formula did is it gave us the slope of the line that connected these 2 points. And so when we were doing average rate of change, we were putting in what was called a secant line, right? So the quality of a secant line is it connects 2 points on a function. So that was average rate of change when we were approximating. We want to figure out how to use the average rate of change to get us to what's called the instantaneous rate of change. So the instantaneous rate of change is how much a function changes at 1 point. So if we can figure out how quickly a function is changing at 1 point, we can figure out how much it's changing at every point and get exactness. So that's our goal here. So the way that we are going to do this is we are going to look at the limit of average rates of change. Remember, the limit lets us get close to something, and we're going to look at smaller and smaller intervals around a particular point. So what we're doing in the beginning is we are trying to find the instantaneous rate of change at a particular point. Once we can do it at a point, we can generalize it to the function. So sort of conceptually, to help you understand the difference between average rate of change and instantaneous rate of change, a good example is to think about driving. So if you consider that it takes you 3 hours to travel 150 miles to your cousin's house, right? So it's 150 miles away. It takes 3 hours for you to get there. Your average rate of change would be 50 miles per hour, right? So it's distance over time. That's going to give you your average rate of change. However, we know that you're not going 50 miles per hour the entire time, right? When you start off driving, you're a little bit slower. Maybe at some points on the highway, you're going a little bit faster. And so your instantaneous rate of change is the reading on your odometer at any given moment. So if you look down and you're going 80 miles an hour, that's an instantaneous rate of change. That's how quickly you are changing at that exact moment. And so when you have a bunch of instantaneous rate of changes, then you can use those to get more exactness. So that's sort of the difference. So we're going to start with sort of a visual representation of what this looks like before we move into the algebra of how we calculate it to help you understand what's happening in the background. Okay. So here we have the function 0.5x squared. That's this parabola right here. Okay. And in this, what I'm going to try to do is I'm going to try to figure out the instantaneous rate of change at -1, right? So -1 is here. And the only tool that I have right now is slopes of lines, right? So we talked about how y equals mx plus b. And so what I did is I looked at the average rate of change at points near -1. Okay, so I used -1 and 0 to get this line over here. And I used -2 and -1 to get this line over here. So how do we get the slope, right? So let's start with -1 and 0, right? So the average rate of change, we're going to do f of b minus f of a over b minus a. And that's exactly what we're going to do here. We're going to do f of 0 minus f of -1 over 0 minus -1. So that's the average rate of change that connects these 2 points, -1 and 0, right? So when I approximate this, f of 0 looks like it's going to be 0 minus, now f of -1 looks like it's going to be approximately 0.5. So 0.5 divided by, now on the bottom, I have 0 minus -1. So the minus and the -1 are going to cancel to give me +1. And so this gives me -0.5. So the slope here, I don't know if you can see, I already wrote it down, but I'm going to write it a little bit bigger. -0.5 is the average rate of change to the right of -1, right? So I used a point to the right of -1. So that's trying to help me approximate by using the average rate of change. But I also want to do this to the left of -1, because just like limits, I want to see what's happening on the left and the right. So when I do it on the left, I have the point -1, that's the point I'm interested in, and something to the left. So here, I picked -2, right? So f of -1 minus f of -2 divided by -1 minus -2. We have to be really careful. There's a lot of negatives here when we're approximating this. So f of -1, well, I said before that I thought that was 0.5 minus, now f of -2, right? If we go here and we try to see what's going on there, so -2, I go all the way up here, boop, 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 boop. I'd say that's pretty close to 2. Divided by, and we do this in 2 steps just to be careful. I have minus -2, so the minus and the negative cancel, right? And that's going to give me +2 here. So 2 plus -1 is going to give me +1. And on the top, 0.5 minus 2 gives me -1.5. So when I crunch that all together, I get -1.5. And so that's my approximation to the left of -1. So notice I use the value at -1 for both my right hand and my left hand guess. And so when we're trying to figure out how much the function's changing at -1, when we do a left hand and a right hand approximation, that's going to give us bounds for what the actual rate of change needs to be. So that means my instantaneous rate of change at x equals -1 is between my left-hand approximation, so -1.5, and my right-hand approximation, -0.5. So what that does is it gives me bounds for where my instantaneous rate of change needs to be. It's got to be in this interval, right? Because I have my left-hand approximation and my right-hand approximation. So the sort of process here, we now tie back to limits, right? This idea that, okay, well, if we can get closer to -1, that's going to make our interval smaller and our approximation better, right? So just like before when we were trying to get really close and we said, you probably don't want to do 1 to 2 if you're trying to get close to 2. The same idea applies here. So I did it with 1 whole unit away to illustrate what's going on, but I actually want to try to get closer to -1 to figure out if I can get my bounds to be closer. So that's what we're going to try here. Okay. So instead of using 0 and 2 as my outer bounds, I'm going to repeat this process, but I'm going to get closer. Okay. And so I want you to try this. So I tried to sort of highlight where it is, but I want you to use these bounds. So -0.5 and -1. So -0.5 is here. I'll try to point to it. So -0.5 is right there. This is -1. And this is -1.5. Okay, so when we do our right-hand approximation, we're going to do it with -0.5 and -1. So I want you to try to approximate based on this graph. This is the 0.5, this is 1. And then you're also going to do it to the left with the -1.5 and the -1. And you're going to do the average rate of change on the left and the right, approximate on the graph, and see what that does to our interval. Okay, so I'm going to give you about 2 minutes to try to approximate it, try to write out what the equation is going to look like for the steps you're doing, and then we'll go through it together. If the TAs are there, they can walk around, and of course, feel free to check in with someone next to you. All right, so take about 30 more seconds to finish up whatever part you're working on. And now let's see what happens when we get closer to -1. Remember last time we were looking between 0 and -1 and -1 and 2. So now we've moved closer to -1. So here, when we do the approximation to the right, we're using -0.5 and -1 as the 2 points to get our secant line. So when we do the average rate of change, f of b minus f of a over b minus a, we need to approximate what these values are. So f of -0.5. So here, right, we can see that that is pretty far down. It's less than 0.5. I approximated it as, let's see, 0.125. If you approximate it as 0.2, that's fine. 0.125 is fine. Somewhere in that general range. I picked that because I sort of did this and I said, okay, 0.25, that looks halfway. And then it looked about halfway between that. That's how I got the 0.125. So if you're in that general range, then we're good here. Minus, now f of -1, that's the one we had from before. We said that that's approximately 0.5, okay? And again, we need to be careful with the negatives on the bottom. So we have minus a -1, so -0.5. This will become +1, right? Because of the minus the negative here. And so we want to carefully plug this into a calculator, or you can do it out if you're comfortable. And I got -0.75 as the slope of that line. Now, again, if you had a different approximation here, this will be slightly different, but it should be in the same ballpark of like, 0.65 to 0.85, somewhere in there roughly. So this, the slope of this line, -0.75. We want to do the same thing to the left here of our -1. So we're using -1.5 and -1. So f of b minus f of a, these are the values we're using. So f of -1, again, we're saying is 0.5 minus, now f of -1.5. Again, you're going to have to do a little approximating. So your approximation might be slightly different than mine, which is okay. But I got 1.125 up here when I tried that out. Yours might be 1.1, 1.2. That's totally in the ballpark, right? And then again, on the bottom, we have to be careful because we have this minus the negative. So this ends up being positive 0.5. And so when I crunch my number there, I get an approximation of -1.25 for my red line here. And again, if you had different numbers than me, this might be slightly different. Okay. So what I want to do is I want to remind you that when we do the average rate of change on the left and the right, that we know our instantaneous rate of change has to be between them. Right? So we know our instantaneous rate of change has to be between -0.75 and -1.25. So in the first example we did, when we were 1 unit away, we had found that we needed to be between -1.5 and -0.5. This was sort of our interval from the first round. If we add in what happened this time by getting closer to -1, right? Now we're saying we have to be between -0.75, which is approximately here, and -1.25. So what we see is that by picking values closer to -1, it gives us a smaller interval where our instantaneous rate of change needs to be. So that means it's a better approximation, right, of what the slope of this line is going to be. So ultimately, and we're not quite there yet, but what we're building up to is that eventually the left-hand approximation keeps getting closer and closer to the actual approximation. And the right-hand approximation starts getting closer and closer. And eventually these two secant lines end up having the same slope, and it becomes one line. So your interval shrinks so much that all of a sudden you're between 2 and 2. So you know it has to be 2. So when we get close enough, what we'll see is those secant lines are going to end up merging into one line. That's sort of where we're trying to get to. And so I want to talk about that one line. Okay. So when that happens, when we get close enough that they merge, okay, this is a picture of what it's going to look like. We get a special line that's called a tangent line. Okay, so remember, a secant line connects 2 points. A tangent line, however, is a line that touches the function at 1 point. So it sort of comes up, it touches right at a point, abuts it, right? And it just touches at that 1 point. We call it a tangent line. And if we are able to figure out the tangent line, the slope of the tangent line is the instantaneous rate of change at that point. So again, the slope of a secant line is the average rate of change. The slope of a tangent line is the instantaneous rate of change. Okay, so again, because we're only touching at 1 point, we can't just use the average rate of change because we only have 1 point to work with. So that's why we're using secant lines to approximate between 2 points until we can figure out the slope of this line. And so it's probably not a surprise to you that once we figure it out, and we'll circle back to this example later, the slope of this line is going to be -1, right? So if you think about the intervals, that's what we are getting closer and closer to. So that's what's happening conceptually, okay? We are using average rates of change to the left and the right to try to figure out the instantaneous rate of change. Now, in the examples that we did, I provided you the intervals that we needed to use. And I will say that it's about 50-50 between when you are given intervals to use to approximate and when you have to come up with your own intervals. So what we're going to do is we're going to do a bunch of different types of examples of this about using the average rate of change in different ways to approximate to approximate the instantaneous rate of change. So the first example we're going to do is with a table, okay? So we have some data, and consider that I've thrown a tennis ball up into the air, and I have the ability to measure the height of the ball in feet for different time intervals. So at time equals 0 seconds, time equals 1 second, time equals 2 seconds. So we can see that the ball is going up, right? It started at 6 feet because right when I let go, the ball is 6 feet in the air because I'm like 5'6", so that makes sense when I let go. Then it goes up to 9 feet, then 11 feet, then 12 feet, and then it comes back down to 10 feet, right? Because the ball starts to come back down. So if we wanted to try to approximate what is happening at 1, I want to know exactly how quickly the ball is traveling at time equals 1. The way that I start this process when I have data on a table is to look at the average rate of change to the left and to the right of 1. Okay, so here's 1. I want to use the data both to the left and to the right. So what I would like you to do is I'd like you to use the data in the table to find the average rate of change to the left of 1. So you'll be using the 0.19 and the 0.06 to find the average rate of change. And then also to the right of 1. So you'll use the 0.19 and the 0.211 to find the average rate of change to the right of 1. Okay, so I'm going to give you about 2 minutes to work out those calculations. Again, feel free to check in with someone next to you, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so when we do the average rate of change to the left of 1, again, we want to embrace this idea of closeness. We are using the closest point to the left, which is this 0, 6 data point. So we're going to do f of 1 minus f of 0 over 1 minus 0. Now remember from 1.1 that f of 1 means we're going to go to our table and get the dependent value. So that's going to be 9 minus 6 divided by 1 minus 0, which is 1. And that gives me a value of 3. And we're going to talk about units in a second, but let's do our other calculation here. When we do the average rate of change to the right of 1, we want to use the closest point to the right, which is this 211 point. So we'll do f of 2 minus f of 1 over 2 minus 1. So f of 2 is 11. F of 1 is 9 divided by, now 2 minus 1 is 1. And that gives me 2. Okay, so before we talk about what to do with these numbers and what they tell us, I want to take a minute to quickly talk about what the units of these numbers are going to be. So what I want to point out here is the values that we're getting in the numerator of this function, the 9 and the 6, right? Those go with the dependent units of feet, right? So these on the top are in feet. And then on the bottom, these are the times, which are in seconds. So when I do this calculation, I end up with a number that's in feet per second, right? This is sort of how we usually notate feet and seconds. Sometimes you see SEC, sometimes you just see S. And so when we talk about rates of change, you usually have something per something. So here we have the dependent units over the independent units, right? They attach directly with the numbers, the 9 and the 6. Well, those are both feet, right? The 1 and the 0, those are both times and seconds. So this is 3 feet per second. Similarly, down here, the 11 and the 9 were in feet, and the 2 and the 1 were in seconds. We are going to do a more in-depth sort of class about units, but here's a good place just to highlight where they're coming from. So what does this tell us? We know that to the left of 1, we were traveling at 3 feet per second, the ball as it goes up in the air. To the right, it was traveling at 2 feet per second. So I know that my instantaneous rate of change has to be between 3 feet per second and 2 feet per second, right? It's got to be in the middle. So there's 2 ways I can think about this. I can say, okay, my instantaneous rate of change, which I'll just write as IROC for space, has to be between 2 and 3, right? Or if I have to make my best guess at what it's going to be, I would average these 2 numbers. So if I average to get my best guess, so I would do 2 plus 3 divided by 2 gives me 2.5 feet per second. Now, this word best is going to be an indicator word. So when you are doing approximations for instantaneous rate of change, sometimes Wiley or Quiz will say approximate using a left-hand approximation. If that were the case here, then my answer would be 3 feet per second. If I'm asked to do a right-hand approximation, right, that's when I use the data point closest to the right. My approximation would be 2 feet per second. If I'm asked for my best approximation or best guess, that's when I do the left and the right and I average them together. So when you see that word best, you should be thinking that you are averaging your results. Okay, so there's sort of three approximations here: the left-hand approximation, the right-hand approximation, and the best approximation, which is the average of the left and the right. So as I mentioned before in our graph, the closer we can get to the value we're interested in, the better our approximation. Now that's problematic on this table, right? Because I can't get any closer to 1. 0 and 2 are the only information I have, and that's as close as I can get. So the only way that I could get closer is if I somehow had a way to measure the ball, right, and where it was in smaller intervals, right? So I'd have to have another table with new data added that had values closer to 1. Right? So I can't do anything on this table. However, let's say for the sake of argument that I was able to get the data at half-second intervals. So here I want you to notice, I'm not sure why that printed so lately, that the same values that were in the old table are still there. So the integer numbers, I'm just trying to trace them a little bit here. Okay, are still there. But now I also have information about where the ball is in the half-second intervals. So here, I now know that at 0.5, the ball was 7.8 feet in the air. And at 1.5, the ball was 10.1 feet in the air. So now that I have better information because I have values closer to 1, I want to repeat this process and do the average rate of change to the left of 1 and the average rate of change to the right of 1 to see how that might improve my approximation. So I'm going to give you 2 quick minutes to again find the average rate of change on the left and the right of 1 using that new data that we have from making our experiment better. Okay, so again, find the left and the right, and if you have time, you can find the best approximation. I'll give you 2 minutes, and then again, we'll do it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so now using our new closer data, let's see how that impacts our interval. I just want to note that, remember, before we were between, let's see, 1 or 2 and 3 in our last was our interval. Okay, and so now that we're closer, let's see what our interval looks like. So f of 1 is 9, f of 0.5 is 7.8. 1 minus 0.5 is 0.5. So that gives me 1.2 divided by 0.5, which is going to give me 2.4. And again, the units haven't changed. So that's 2.4 feet per second. Okay. Now, when we do that approximation to the right, we're going to be using the 1.5. So f of 1.5, we get 10.1 minus f of 1, which is 9, divided by 0.5. So that's going to be 1.1 divided by 0.5. And that gives me 2.2 feet per second. So before, when we did a whole unit away, right, when we were jumping between 0 and 1 and 1 and 2, we were between 2 and 3. Now our interval is between 2.2 and 2.4. That's a significantly better interval, right? If we were going to do a best guess here, we would average those and we would get 2.3 feet per second, right? So that's different than our best guess before. Our data is better, so this is more accurate, right? Our interval has shrunk, and now we know that the exact rate of change, the instantaneous rate of change, is closer to 2.3 than 2.5, okay? Now, just like before, the only way we would be able to make this better is if we could get data closer to 1, right? And so we'd have to have some really precise instrumentation, but let's say for sake of argument that our instrumentation was super duper good and we were able to calculate to the 1/100th value here, closeness to 1, right? So again, we know at 1, we're moving at, we have a height of 9, but now we know what's happening at 0.99 seconds and 1.01 seconds, right? If that was the case, we would be super close to 1. And so when we did it to the left, we'd have f of 1 minus f of 0.99 divided by 1 minus 0.99. Right, we would do this on our table, so we'd have 9 minus 8.976355 divided by 0.01, okay? And when we did that, we would end up with 2.3645, and again, feet per second. And when we did our approximation to the right, we'd have f of 1.01 minus f of 1 over 1.01 minus 1. So we take those values, 9.02365 minus 9, f of 1 is 9, divided by 0.1. And we would get 2.3645 feet per second. So up to 4 decimal places, we are accurate and have the same value, which means that the instantaneous rate of change is 2.3645, right? That's as close as we're probably going to get. That's really, really accurate. And so what this is meant to do is to highlight to you that if you are able to get close to 1 in the same way we got close as limits, if you're able to get that data, then your approximations are going to be far, far more accurate, right? We knew from before that we had to be between 2.2 and 2.4. And this is certainly between 2.2 and 2.4. But we can see a little more accurately exactly where it is. So again, if you have a table, you don't really have the choice of how close you are. You're going to use the closest point. But you can imagine that if we were working with a function, right, if I had just given you a function to plug into, we would want to pick points really, really close to the point we were interested in, okay? So that's sort of a data visualization on a table. And so now we want to do some more formal language around the instantaneous rate of change, okay? So it turns out that there's a lot of different ways that we talk about the instantaneous rate of change and the different notation that we use. So another way that we talk about the instantaneous rate of change. So that's one set of words that we use to talk about it. We also call this instantaneous rate of change the derivative of f of x at a. So when we talk about approximating the rate of change at a point, we could also use the word derivative. So the derivative at 1 was 2.3645. Okay, so what's important at this point is that what we are learning is how to approximate it at a particular point. Okay, so we're doing this at 1. We were doing it, before at -1 on the graph. So we're only learning how to do this at a point for now, and then we'll generalize it later. So how come we have different ways to talk about the same thing, right? So the instantaneous rate of change, same exact thing as the derivative. So the reason why we have different ways to talk about this, and this is going to come up with both the notation and the words, is that calculus was invented by two different people at the same time. So Isaac Newton and Leibniz were both developing calculus simultaneously in the late 1600s. And there was a whole lot of controversy about who did it first. So Newton said he did it first, and he accused Leibniz of stealing his work, but Newton hadn't published it, and so Leibniz had published it, and it was like a whole thing. And so basically it created this like war of sides, like the Newton camp and the Leibniz camp, and it never really got settled. And so what that means for us is that we have two sets of notation, the notation that Newton used and the notation that Leibniz used, and we still use both, 300 years later, which is a little bit crazy. But that's why we have two notations and two sets of wordings for all the stuff that we'll talk about in terms of rates of change. So instantaneous rate of change is the same thing as the derivative. So we are often going to see it notated like this, f prime of a. So this little prime says that we're looking for the rate of change, what's called the first derivative. We will talk about what's called a second derivative in a couple classes from now, but we're looking for the derivative at a. So for example, what we were doing up here, we were looking for f prime of 1. We were approximating the derivative at 1. Okay, this is from Newton. This is his notation. We will also later see that we can write this, and this will come up probably in the next class, as dy dx, and that's the Leibniz notation. I don't know if there's a T at the end of his name. There may or may not be a T. We mostly use Newton's notation, but later on in 2.3, when we talk about units, we will also use some of Leibniz notation. Okay, so we want to start getting comfortable with the notation when we're working on problems. And so we're going to be doing some more practicing on finding this derivative, aka instantaneous rate of change. And we're going to try to bring in some of the notation so that you're comfortable seeing it and understanding what it's asking you to do. Okay, so let's go on to a new problem here. Okay, so here I have a table that has values 1, 2, 3, 4, and 5. And what I would like you to do is I'd like you to use the table below to approximate the instantaneous rate of change for the value at 1, 2, 3, 4, and 5. So for each of the values represented on the table. So what I recommend that you do is to start by finding the average rate of change between all the points. And then from there, if you can do a best approximation by averaging things to get the approximation for the derivative. Okay, so I'm going to give you about 3 minutes. Again, I would start with the average rate of change between each of the points. So between 1 and 2, between 2 and 3, between 3 and 4, between 4 and 5, and then use those to talk about the instantaneous rate of change for each point. Okay, so take 3 minutes. Feel free to work with someone next to you, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right. So what I did here is I did the calculation between each of the 2 points. So for example, if I was looking for the average rate of change from t equals 2 to t equals 3, I'm going to do f of b minus f of a over b minus a, which is the change in the dependent values over the change in the independent values. So here that would be 31 minus 16 divided by 3 minus 2, which gave me an average rate of change of 15. And so I did that for all the points. And so I got 9, 15, 21, and 27 when I did those calculations. So what I want to do is I want to figure out how to translate those into instantaneous rates of change and approximations. So here, I'm going to start with f prime of 1. I'm going to use the approximation symbol just to note that it is an approximation since I don't know the data completely. And so 1 and 5 are a little bit more tricky because we don't have a left and a right hand approximation, right? So for 1, we only have a right hand approximation, the value between 1 and 2. So that is the best that I can do with the information I have on this table. I can't construct extra data over here because I don't even know where this data came from. So my approximation for the instantaneous rate of change at 1 is just going to be 9, which is the right-hand approximation, which was the average rate of change between 1 and 2. Okay. However, when I approximate the instantaneous rate of change at 2, I do have the ability to have a left-hand approximation and a right-hand approximation. So I have 9 and 15. So this is where I'm going to average those two numbers. So I'm going to do 9 plus 15 divided by 2. And that's going to give me an approximation of 12. Okay. I'm going to circle back to that in a few minutes, but let's keep going here. So f prime of 3, the instantaneous rate of change at 3, well, I have a left-hand approximation and a right-hand approximation, so 15 and 21. So I'm going to average those. 15 plus 21 divided by 2, so that's 36 divided by 2, and that's going to give me 18. My approximation at 4 for the instantaneous rate of change. So again, at 4, I have a left hand and a right hand approximation. So I can average those together. So 21 plus 27 divided by 2. So 48 divided by 2. That's going to give me 24. And then last but not least, I'm going to go for the derivative at 5. And again, I only have one approximation. For 5, I only have the left-hand approximation. So I just have to use that to make my best guess. So f prime of 5 is 27. So that's how we start approximating instantaneous rates of change on a table. I do want to point out one shortcut that if you are comfortable using it, you can, but you don't have to. And I'll just do it for 2, but it would apply for any of the middle values. So if I wanted to approximate the average rate of change on the left and the right and average them together all in one step, what I can do is I can look at 2 and I can use the data point immediately to the left and immediately to the right and do the average rate of change for those values. So here that would be 31, which is the value to the right, minus 7, the value to the left, divided by 3 minus 1. Okay, so 31 minus 7 is going to be 24 divided by 2, which is going to give me 12. That's the same value that I get if I do the left-hand approximation, the right-hand approximation, and I average them together. You can do it in one step by doing the average rate of change with the 2 points next to the value, and you get the same outcome every time. So mathematically, they are equivalent. So if you don't want to have to do the left and the right every single time, you can just use the 2 points around it to get the same ending best value. Okay. So that's how we do this, again, on a table using our new notation to talk about those values. Again, the number in here was the independent value from up top. And then over here, this was our rate of change. Okay, so again, the values that we're getting here, these are not dependent values. These are not the values from the table. These are approximations of the rate of change. So that's in line with the calculations we've been doing. Another sort of important step in our journey with derivatives here is to start this idea of how do we determine if the derivative is going to be positive, negative, or zero, okay? And we're going to do this a whole bunch next class, but this is just sort of a tiptoe into it to practice once. So there's 5 derivatives listed here. We have the derivative at -2, the derivative at -1, the derivative at 0, the derivative at +1, and the derivative at +2. And so what we want to do for each of these is determine if the derivative value will be positive, negative, or 0. We are not looking for the number, so I'm not looking for -5. I just want to know, is it positive, negative, or 0? And so what we want to do is we want to connect this back to the tangent line. So we'll do the first one together, and then I'll have you try the others. So f prime of -2. That means I need to figure out where -2 is in terms of my function. So that's here. I go to -2, I go to the function, and then I have to picture what the tangent line is roughly going to look like. Okay, so my tangent line is going to look like this in general. And so if it is downward sloping, then the slope of that line is negative. So since it goes down from left to right, the slope of that line has to be negative, which means my derivative has to be negative because the derivative is the slope of the line. So what you want to do for each value is look at the picture, try to picture what you think the tangent line would look like, and then determine if the slope of that tangent line is positive, negative, or 0 at each of these values. Okay, so take 2 minutes, try to look at it. You can sketch it out, whatever you need. But again, just positive, negative, or 0, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's take a look at these. So f of -1 means I'm going to go to -1. I'm going to go down to the function, and I'm going to try to envision what the tangent line would look like. So a line that only comes up and bumps it up in that one spot. So it's going to look approximately like this. And then I have to determine, is the slope of this line positive, negative, or 0? Since it's going upwards from left to right, the slope of that line is positive. So my derivative is going to be positive. Excuse me. In a few classes from now, we're going to be learning how to approximate the value of this line, right, numerically. But for right now, we're really just concerned with whether it's positive, negative, or 0. So at 0, we have this instance where when I draw on the tangent line, it's horizontal. Okay, it sits right on top and it lays horizontal. The slope of a horizontal line is 0. So that one has a 0 slope. It's not going up or down. Then at +1, the tangent line looks approximately like this. So it's downward sloping from left to right. So if it's downward sloping, that tells me the derivative is negative because the slope here should be negative. And then finally at 2, I'm right about here. My tangent line looks like this. I can see that that's going up from left to right. So the slope of that tangent line is positive. So one of the things that we will often do in this class is positive, negative, 0 when evaluating derivatives, or you can do this with average rates of change, right? So if I asked you about, let's see, the average rate of change from, let's say, negative 0.5 to 0, right? So negative 0.5 is here, 0 is here. So the average rate of change is the slope of the secant line. That goes up from left to right. So that is positive, right? So we can ask a lot about all the different lines we're looking at. So it's important that you're able to visualize those lines, whether it's a secant line from average rate of change or a tangent line from the derivative, right? So positive, negative, 0 is a really good analytical tool to help you figure out a lot of things. Okay, so moving on from that example where we're sort of picturing tangent lines, we now want to step into the space where we are going to take functions and we are going to try to approximate the derivative at a point. Okay, so here we are considering the function 4x squared, and we are interested in finding the derivative at 3. So the tools that we have right now in order to be able to approximate the derivative is by using the average rate of change to the left and to the right of the point that we are interested in. And again, we want to try to get close to that point. Now, how do we do this with a function versus, say, a table or a graph? So the way that we're going to approach this is by creating our own table, right? So there's no reason why we can't create a table. So what we're going to do is we're going to put our independent values on the top and our dependent values on the bottom. So how do we generate this? Well, 3 is the point that we are interested in. And so if we take 3 and we plug it into the function, we get 3 squared, which is 9, times 4 is 36. Then we want to pick something close to the left and something close to the right. I'm going to let you pick those values based on what we've talked about in terms of closeness. But once you've picked your close value on the left and the right, you're going to need to plug those into f of x to get the dependent values. And then you will do the average rate of change to the left and the average rate of change to the right to get your approximation for the instantaneous rate of change. Okay, so I'm going to give you 2 minutes. Okay, so pick a value that you think is close to 3 on the left, close to 3 on the right. It should be the same distance away. So if you pick, 2 over here, you would pick 4. So it's 1 unit away. If you pick 2.9, right, that's 1/10. This should be 3.1. So make it the same distance on either side. Again, once you have the values you've picked, plug them into the function to get the dependent values. Then we'll do average rates of change on the left and the right. Okay, so try that out and we'll work through it together in about 2 minutes. All right, so let's take a look at this because there's sort of a lot of context and wording here that's going to be really important. So this was the first time that we got to pick how close we are on our own. I decided to go to the 100th place. That's sort of where I typically go. You may have chosen 2.9 and 3.1. That's totally fine. If you picked 2 and 4, that might be okay depending on the problem, but sometimes you might have to repeat it to get closer depending on your choices for the approximation. So obviously, if you pick different values than me, your numbers are going to be slightly different, but should be in the same ballpark. So I picked 2.99 and 3.01. I got the corresponding dependent values by plugging those values into the original function. And then once I had them, I did the average rate of change to the left and the average rate of change to the right. So I got 23.96 and 24.02. Okay, so here I would say I would probably call this approximately 24, which is right sort of in the middle. It's going to actually be something like 23.99. But I'm going to call that 24 just to round to a whole number. So within the context of this problem, there are a lot of ways that this can be asked. So it could be asked exactly like you see here, approximate the instantaneous rate of change. And then as it's worded, you can do it just like this, right? However, sometimes you may see wording like approximate the instantaneous rate of change to the left using, and then something like delta x equals 0.01. Okay, so what does that tell you? That tells you that I'm only doing a left-hand approximation and that I need to be within 0.01 of the value I'm interested in, so of 3. So if that was the way it was worded to the left, using delta x equals 0.01, I would need to use 3 and then a value right to the left of 3 that was 0.01 away. So that's the 2.99. And so my answer would be 23.96. I would only do the left-hand approximation, right? If it said to the right using delta 0.01, then I would just do the right-hand approximation. If it said to the left using delta x equals 1, I would plug in a 2 into this function and use 2 and 3 as my values. So you have to be really, really careful about what the instructions are telling you to use as your values, especially on mini quizzes and chapter quizzes. This is something that comes up often that students get wrong because they do the entire approximation. Okay, so try out the other 2 examples on your own. And on Thursday, we will learn more about the derivative function and how to draw it.